Faster attention is what you need. A fast, self-attention neural network backbone architecture for the edge via double-condensing attention condensers. In this work, we introduce a new, faster attention condenser design called Double-Condensing Attention Condenser, DCAC, which enables more condensed feature embedding. We then incorporate this design into a machine-driven acceleration strategy to yield a new highly efficient backbone architecture called AttendNext. By being fast, accurate, and having a low memory footprint, we find that this backbone architecture is well suited for ML applications on the edge. Many key emerging technologies, such as autonomous driving, automated industrial inspection, and augmented reality applications require on-device deployment of deep neural networks. However, these neural networks require significant computational resources, making them challenging to deploy on edge devices. This need for more efficiency has propelled research into efficient deep learning for resource-constrained devices. One strategy has been the concept of attention condensers used in architectures such as the TenNets, which are self-attention-based neural networks which have a low footprint yet are highly efficient. In this work, we build on attention condenser networks by introducing a double-condensing attention condenser (DCAC) self-attention mechanism. Compared to the traditional attention condenser, the DCAC introduces an additional condensation mechanism on the input features V, which enables improved network efficiency. It also streamlines the attention condenser design by removing the scaling conducted during selective attention F. There are three main components to the DCAC module. The input features are first passed into the condenser layer, which condenses the input V such that greater emphasis is placed on the activations near strong activations. Next, the features are passed to the embedding layer, which learns condensed embeddings characterizing joint local and cross-channel activation relationships. Finally, the expansion layer projects the condensed embeddings to the appropriate dimensionality. The resulting self-attention values A and feature embeddings B are then leveraged to perform selective attention. Having designed this key module, we employ a machine-driven exploration strategy which leverages generative synthesis to determine the macro-microarchitecture design. This method is formulated as a constrained optimization problem, where the goal is to find the optimal generator G star which generates network architectures N that maximizes a universal performance function under a given set of operator constraints. This optimization process is performed iteratively via the interplay between the generator and an inquisitor, which is responsible for assessing the performance of the generator via its generated architectures. To obtain architecture designs that exhibit a desired balance between accuracy, architectural complexity, and computational complexity for edge scenarios, we enforce four design constraints. First, we encourage architectures with parallel columns. Second, we restrict the use of pointwise striated convolutions. Third, we urge the use of anti-alias downsampling modules. And fourth, we enforce the top 1 accuracy on ImageNet for a validation set to be above 75.8%, to be at least on par with the performance of the once-for-all 62 architecture. The machine-driven exploration strategy thus results in the AttendNext architecture shown here. Note how it is comprised of 4 heterogeneous columns and incorporates both the AADS and the DCAC modules. The DCAC modules help improve representational efficiency by enabling efficient selective attention. The AADS modules found throughout the architecture improve robustness and stability by making it more shift invariant. We also find that different degrees of columnar interactions at different stages help strike a balance between accuracy and efficiency by learning representative yet disentangled embeddings. We evaluate the accuracy of AttendNext in the remission dataset and profile the performance on a Raspberry Pi edge device. Across 3 metrics of top 1 accuracy, model size, and relative inference throughput, we find strong performance for AttendNext when compared with existing state-of-the-art efficient architectures. For example, AttendNext obtains much higher inference throughput, including up to 10x faster speeds compared to FBNetC and Mobile One S1. It also achieves a top 1 accuracy of 75.8% on ImageNet, which is comparable to other architectures while being significantly faster. AttendNext also has a much lower memory footprint, coming in at significantly smaller than once-for-all 62, MobileNet V3L, FBNetC, and Mobile One S1. In conclusion, by demonstrating a strong balance between accuracy, architectural complexity, and computational complexity, Attendix shows that further exploring different efficient architecture designs and self-attention mechanisms can lead to other interesting new building blocks for TinyML applications. We would like to acknowledge the Natural Sciences and Engineering Research Council of Canada for supporting this research. Thank you.